Good morning, everyone. It's good to be with you here on the last day of spring quarter. Always a blessing, but today is kind of that special bittersweet end of the quarter time. Um, I think that when I think back on this quarter, um, I'm guessing at least until I go senile, that this will be a time that I'll be remembering. Probably for the rest of my life with this whole COVID season, and we don't really know where it's going. Um, but I'll probably be remembering lots of difficult times and adjustments and things that were going on in the world. But I will certainly be remembering the time in class that we had going through. I don't know where this stacks up, but certainly some of the harder material that's in the Highline curriculum. And doing it with all of you and meeting with all of you and kind of wrestling through some of the questions about the world, both kind of at a health level, at an economics level, and now in a social justice context. So, uh, you know, I would love to say that I remember all my students, every student for all time. I don't think I can say that that's true any longer, but I do think that I will be remembering this class and this experience. And so even if it's 10 years down the road, all you probably have to do is say, hey, Dust, remember when we were together during COVID in Zoom class and we were all figuring it out together. And it'll bring back some mostly fond memories. This is my first real experience teaching online, and I've appreciated how gracious you have all been with me as I've tried to figure things out, as we've adjusted systems to try to make them work for you, work for the material. Lots there, but really, yes, the math is important, but really, it's the relationships and the conversations have been good, and I've appreciated the window that you have allowed into your life, kind of some of the good times and some of the struggles. Very good. Very good. Well, then let's go and look at the end of the divergence theorem. Let's just begin by just glancing at the last example that we worked through. So in this last example that we worked through at the end of class yesterday, we had this cube. It had 6 sides on it, and we wanted to find the flux. And so since we were trying to find the flux, we sort of had 2 options. Option 1 was to do it directly. And if we did this directly, this would require parameterization, and we would have to parameterize how many times?
6.
6 times, right? Parameterize 6 times, which sounds maybe not difficult, but definitely like a pain and tedious. And so the other option is to use the divergence theorem, and this would be 1 triple integral. And so this made us smile a little bit. So we wanted to calculate our flux. We wrote this as a triple integral here. We had the divergence of our field that was up above, and we evaluated the triple integral, and we came out with the 6. The 6 represents the flux. And as we talked about yesterday, you can visualize that flux as being kind of the amount of stuff that's either going into the box or going out of the box. In this case, since it's a positive 6, since we're oriented outward, that means that there's 6 units of stuff leaving the box per unit time. At least that would be one way of interpreting this. Questions about that from yesterday? Very good. All right, so there's one more note here before we go on to the next example. So with Stokes' theorem, rotation fields are noteworthy because they have non-zero curl. With the divergence theorem, the situation is reversed. Pure rotation fields have zero divergence. However, with the divergence theorem, radial fields are interesting and have many physical applications. So it's kind of wordy. Let's make sure you're understanding what's going on. So if we have a field that's rotating, then we would say that in this case, the curl would be greater than 0, and the divergence would be 0, I mean, at a simple level. Over on the other side, say we had a radial field, something like that. Here, the curl would be 0, and the divergence would be greater than 0. And so remember, which theorem is it that focuses in on curl? Which of our two concluding theorems?
Green.
Green's theorem focused in on actually both of them. There are two versions, but of our last two theorems that we've been talking about, which two? So what's the 3D version of Green's theorem?
Stokes.
Yeah, so this would be Stokes' theorem. And so what this statement below is telling us is it's saying Stokes' theorem is interesting here on the left and not very interesting here on the right. And then which theorem is focused in on divergence? This is the tough one, right? This would be our divergence theorem. And the divergence theorem would be interesting here on the right with the radial fields and not interesting with the rotation fields. Does that make sense? You might ask, how do I know which is which? And the text does a really nice job of walking through that stuff. And we've addressed this a little bit in the past, but one simple thing is that when you have all of these components of the field are all the same sign, like this is one super easy way of identifying what's going on. When all these are the same sign, that's an indication that you may have a radial field, something that's spreading out. If you have things where like some are positive and some are negative, that's what's going to start to give you that rotation bit. In this case, I don't know how the square would impact things. All right, let's go on and do another example. So let me talk through it and then we'll switch over to our DocCam. So let S be the surface of the solid enclosed by the circular cylinder x squared plus y squared equals 9 and the planes z equals 0 and z equals 2 oriented outward. So we're going to use the divergence theorem to find the flux of the vector field F equal to x cubed y cubed z squared. Remember that whenever you see flux, you should at least consider using the divergence theorem. So these two things are tied together. Let's switch over to the DocCam. All right, so we have this surface S that's enclosed by x squared plus y squared equals 9, z equals 0, and z equals 2. It's oriented outward. Here's the field, and we're trying to find the flux. Maybe we could draw a picture. It's not necessary, but sometimes it can help us to see what's going on. So we have this cylinder, and the top of the cylinder would be at z equals 2. And the radius of the cylinder looks like it's 3. Okay. And it's oriented outward. So a positive answer will tell us things going out of the can, so to speak, instead of into the can. Okay, so we want to find the flux, and the flux is equal to the surface integral of F dot n. Remember, flux is the normal component of the field across the surface, ds, and this is the big S. And if we were to calculate this directly using the surface integral, how many different surface integrals would we need?
Three.
We would need 3. One for the top, one for the bottom, and one for the outside. So we'd need 3 different surface integrals to actually figure out what that flux is if we were to do this directly. So that sounds like a lot. So let's try using the divergence theorem. So maybe I'll call this thing the can, the inside of the can. And we want the divergence of F dV. So let's figure out what that divergence is. So partial derivative with respect to x will be 3x squared plus partial derivative with respect to y, 3y squared, plus partial derivative with respect to z of z squared is 2z. And all this is dv. What coordinate system would you like to use to work through this cylindrical question?
Cylindrical?
That was a good guess. I like it. So let's use cylindrical coordinates. So if we use cylindrical coordinates, the 3x squared y squared here, or 3x squared plus y squared, could be written as what?
3r squared.
3r squared. The 2z,
2z.
excellent. 2z is still 2z. dv,
R dz d d theta d dr d theta.
maybe the order matters, maybe it doesn't. In this case, it won't make a difference. Well, won't make much difference. So our z's are going from 0 to 2. Our thetas are going 0 to 2 pi. Our r's are going from 0 to 3. Are there any questions so far? Thanks for the couple thumbs up. That looks good. All right, so now we just get to crunch through and see what happens. Notice there's no thetas anywhere in sight in this integrand or in the limits, and so we know that that whole 0 to 2 pi is just going to all evaluate to just a 2 pi out front in our integral. So we can save ourselves a little bit of computation that way. So this will be equal to 2 pi, and maybe we'll integrate with respect to z first. So I've got 0 to 3, 3r squared z plus z squared. Oh, I forgot the r. I'm sorry. I lost track of this r right here. So let me go back. So we have 3r cubed plus 2zr dz dr. Everyone okay with the 2 pi out front? So this will be 2 pi integral 0 to 3, 3/4 r to the 4th plus z squared r.
No, we're integrating with respect to z.
Oh my gosh.
So the r.
Yeah, you're correct. We wrote them down in the reverse order, so I'm trying to change from what I did in my notes, and I'm clearly thrown off my gain. So this would be, oh my gosh.
But you had the second one, right?
Yeah, this exactly. I'm like just making up what I'm right at, what I'm good at, and what I'm not good at. Thank you all for being so gracious. So 3r cubed z plus z squared r from 0 to 2 dr. Did I get that? It's a little chicken scratchy, but does that work?
Yeah.
Okay, excellent. So 2 pi integral 0 to 3. So this will be 6r cubed plus 4r dr. So now we can integrate with respect to r. Going from 0 to 3. At 0, again, everything will be 0. So we have 2 pi 3/2 times 81 plus 18, which, if I did my arithmetic earlier, let's see if this all works out. It's 279 pi. So that lines up with the notes, but does that line up with your calculations as well? Got one thumbs up. All right, so that's a whole bunch of calculations. And I think sometimes in all those calculations, we can lose track of what it is, like what's the big picture. So let's go back to the notes and so we can see the whole question all at once and make sure that you're seeing what the big picture is of what we're doing. So we are trying to find the flux. So we're trying to find our flux across this surface here through this field. And so remember, that'd be the amount of stuff that's entering or leaving the solid. And so to calculate the flux, we use our surface integral here. That looked like a pain because if we were to do this directly, we would have to evaluate 3 different surface integrals. And so we said, oh, that looks like so difficult. So let's try the divergence theorem. And the thing that lets us know that we can use the divergence theorem with no reservations is that we're looking for flux, and it's the surface of a solid. So just to be clear, if you were trying to find the flux across a surface S1, the divergence theorem wouldn't really work because this isn't a solid. But if you were trying to find the flux across some funky solid or surface S2, then the divergence theorem wouldn't would apply. So down at the bottom, you could do it directly. or you could try the divergence theorem. I don't know if you guys could see the very bottom of the writing here. But up top, you would only be able to find the flux directly because it's not a closed surface. Okay, so we tried our divergence theorem. We went through all these calculations. And at the end of all that stuff, we got this number 279 pi. And this 279 pi basically tells us how much stuff is leaving the cylinder. So like the rate stuff, and we don't really know what stuff is in this case, but is leaving the cylinder. Questions about the solution or the interpretation of this result? Very good. All right. We have one more question, one more example. It's not much more difficult than this, but I'd like to work through it. But before we do that, I just want to make sure that there aren't questions about what you need to do and deadlines and structures. So I'm going to actually put you in breakout groups just for a couple of minutes. And the purpose of these breakout groups is simply to ask, do you have questions about what you need to do for the remainder of the class? So you have questions for what to do before the end of class. And I don't mean today, but I just mean in general. And I just want to touch base with each other, make sure you ask, make sure everybody speaks up a little bit. I just want to make sure that we don't miss something because someone's shy to speak up in the large group. So one last time, just some quick breakout rooms for 2 minutes. Welcome back.
Thank you.
I had an idea to just do like a Zoom study group on Sunday. I could host it and everything, but I figured I'd just post on Slack and people could say when they were available or something. Would that, like, is that okay with you?
It's okay with me.
Okay.
Is this all about putting it out there and seeing how many people want to do it?
Yeah. So because I think like I'm free after like 1 or so, but then like I'm sure some people couldn't make it till the evening or things like that, but it could kind of just be open as long as it needed to be. People could just work as long as they wanted. So
what would be the focus of the study group?
I mean, probably mainly assessment, but also I figure since the homeworks are due that day, like I kind of just figure like if we get enough people there, then there will be someone who has done everything. Like there'll be one person who's done this problem and one person who's done this problem, so people can kind of just explain stuff to each other, hopefully.
The ponies are really important. Yeah.
Very important.
Yeah.
So, yeah.
Can you give a thumbs up if you think it's a good idea to have a Zoom study group on Sunday? I'm seeing check marks and thumbs up. That sounds like a go, and probably goes without saying. But if somebody else wants to do something on Saturday, by all means. And does it work to post it on Slack then, Melissa?
Yeah. I'll just ask what times people are free and then just kind of post a link based on that.
That sounds good. Cool. Robert, so you're unmuted. Didn't know
Yeah,
that was...
no, I'm just.
Cool. Just wanted to make sure there weren't other thoughts there. Were there any other thoughts or questions that came out of, nice, Dean. Any other thoughts or questions that came out of the small group? Very good. Civ 6? What is Civ 6, Enrique? Oh, got it. Video game. Got it. I'm tracking.
So the final is due on the day of your presentation, or are they all due on Monday?
I've actually gone back and forth a whole bunch in my brain with this. I have them all due on Monday.
Okay.
And I think my reasoning, my thought process was that I didn't want to incentivize people choosing the last day for presentation simply so that they had 2 more days to work on the assessment. I could probably be talked into something a little different, but I guess my question, it would be sort of a question to you. Does that seem like a reasonable approach, or do you think that we should adjust that?
That seems reasonable.
Yep.
Okay. Yeah, so the assess, go ahead.
Croy,
Go ahead, Croy.
you should have had us sign up for the due dates and then told us it was due on the presentation. We wouldn't have known.
Yeah, I could have done that, but I didn't. Titus, thoughts?
I just have a question. Is there going to be late penalty for assessments?
Yeah, so this is the other thing, is there's a 2-point penalty if you turn it in by Wednesday at 2 p.m. So the other way, and that's going to be on, I mean, the whole thing will be worth 80 points or something like that. So it's a relatively minor penalty. And so the other way of looking at it is to say, if you're to max everything out, you've got to get it in by Monday morning. But there really is a relatively minimal penalty if you were to turn it in the day of your presentation, for example.
Sounds reasonable.
Cool. So there's a little bit of freedom both ways. Any other questions? It's actually been more fruitful than I was expecting. So I really appreciate your questions and also the suggestion for the study group. Anything else question-wise or structure-wise that came out? Very good. Let's look at one last example. And I think it's pretty straightforward, so maybe we won't use the doc cam for this last example. So here we want to let S be the surface of the solid enclosed by the hemisphere, Z equals root A squared minus Y squared minus Z squared, and the plane Z equals 0, oriented outward. We're going to use the divergence theorem to find the flux of the vector field across S. One note before we dive in, if we just had the hemisphere, then would we be able to use the divergence theorem? Like, it was like this, and there was no bottom.
No.
So if there was no bottom, but I don't know about you, I actually really like the divergence theorem. So frankly, I'm really sad when I can't use the divergence theorem. So what if there'd been no bottom, how might we have adapted this stuff so we could still use the divergence theorem?
Did you take another integral and subtract the bottom from that divergence theorem integral?
Exactly. So it's almost this. I don't know if it's kosher to write it this way, but I could have said that this would be equal to the triple integral of the hemisphere with the bottom minus the surface integral of, am I allowed to say like this, minus the surface integral of a disk? Is that acceptable notation, or at least clear what would be happening? And so we could sort of combine the two things to be able to still use the divergence theorem. And the advantage of this would be, rather than having to parameterize some hemisphere, which is not difficult, but a little bit of a complicated parameterization, we could simply evaluate a triple integral and then subtract off a super easy parameterization across the disk on the XY plane. Does that make sense? Very good. Okay. So let's look at this particular question. So we want to evaluate the flux. And so again, our formula for flux is it's a surface integral of f dot n ds. Just remember that flux is tied to the normal component of the field. Circulation was tied to the tangential component of the field. So we want to find our flux. That looks complicated. So good news for us, it's a closed surface, so we can switch from the surface here to the solid and use the divergence theorem. And so in this case, we got this nice clean formula for the divergence, and we have a hemisphere. And so what coordinate system should we switch to? Use which coordinates?
Okay. Spherical.
So we're going to use spherical coordinates. So the nice part about this example is the previous example reviewed cylindrical coordinates. This one reviews cylindrical coordinates a little bit. And so our x squared, y squared, z squared is going to become this rho squared. And then the rho squared sine phi, this is our what? What do we call this thing?
Scaling factor?
Exactly, that's our scaling factor. And this particular integrand is nice integral is nice because you have only constants in your limits of integration and you have a product. And so we can just split it up into 3 different parts. And so the rho stuff, you have the 3 is out front. Your rho to the 4th is going to become a rho to the 5th over 5. That's your antiderivative from 0 to a. There's no thetas at all, so your antiderivative is just theta from 0 to 2 pi. Antiderivative of sine, negative cosine. Ooh, typo here. This should be phi. From 0 to pi over 2. And we crunch through all that stuff, and we come up with this result, 6 over 5 pi a to the 5th. The 6 over 5 pi a to the 5th, this represents our flux, or if you will, it's the amount of stuff. This is like the stuff, or the rate at which the stuff leaves the hemisphere. Could A be negative?
Good.
Could we have the A here be negative?
Yes.
Yeah. From a
Yep.
mathematical standpoint, yeah. Any no's out there? What is it?
Radius, right?
Exact. That's the thing I was looking for. What does A represent?
Radius?
Yeah, it's the radius of the hemisphere. And so since it's a radius, it's not that you couldn't have a negative radius, but it's really difficult to buy those at the store. So it seems unlikely that it would be negative. So stuff is leaving the hemisphere, not coming into it. Any questions about this example? What store do you buy positive radius at? That's a good question. You can buy positive radius at Lowe's and at Home Depot, but only Lowe's sells negative radiuses, so because they're low. All right. Yeah. You can buy patience at the store. It just, you have to be willing to wait in line a long time. Okay. Let's see if we can wrap this stuff up. We've reached the conclusion of calculus.
Wait.
Whoa, you okay?
No, I missed a
Russian.
chemistry quiz today.
Oh no, I'm sorry to hear that.
Oh, sorry. I thought I didn't know I was not muted. Sorry.
It's okay. I'd encourage you to reach out to your instructor. So we reached the conclusion of calculus, at least until you seek out a more advanced course as part of your studies. And rather than ending with just the theorem and some examples, I'd like to pull this excerpt from another calculus text by a guy named George Simmons. It's not a great book. It's old-fashioned-y. It doesn't have WebAssign or MyLabs or any of those things, but it was pretty well written, and it had a really nice conclusion. And so to gain a slight glimpse of the significance of what we've been doing, you'd like to look briefly at Maxwell's equations from the 1860s. Some of you have taken physics. Y'all know a little bit. Those of you that have physics know a little bit more about electricity and magnetism probably than I do. But nevertheless, I think this is a valuable thing even for those of us that haven't had a chance to do it. So all the known phenomena involving electromagnetism can be explained and understood by means of Maxwell's equations. And so there's at least, sorry, Croy. Yeah, you're back in physics 202. There's at least 3 different representations for these same things. So there's multiple ways of saying these equations, but the basic gist is that the first equation is that this surface integral of E, and that would be the electric field dotted with N dA, would be Q. I think that's the total charge divided by E naught. And this is E naught's just some constant. So you could interpret this as the flux of the electric field through a closed surface is the charge inside the field divided by that constant. The second equation is that the line integral across the electric field is equal to negative the rate of change with respect to time of the magnetic field, or the normal component of the magnetic field, across the surface. So the line integral of the electric field around a loop is equal to the rate of change of the flux of the magnetic field. The surface integral of the magnetic field, I'm sorry, I don't think I said, it's listed down below, but E would be the electric field. Electric field. And then what is B again?
Magnetic?
Yeah, the magnetic field. Okay. All right. So the surface integral across the magnetic field, or at least the normal component of the magnetic field, is 0. The flux of the magnetic field through a closed surface is 0. And this should tie back to this idea that with the magnetic field, it's wanting to rotate, it's not wanting to diverge, I think is what that's saying. And then the last is a complicated expression, but it says the c squared, this would be the square of the speed of light of the circulation about the magnetic field, is equal to 1 over this constant times the surface integral of J. And this J here is the current density. It's not talking about the unit vector, dotted with N dA, plus the rate of change with respect to time of the normal component of the electric field. Square of speed of light times the integral of the magnetic field around a loop is equal to the current through the loop over E plus the rate of change with respect to time of the flux of E through the loop. Those are Maxwell's equations. Talk to your Physics 202 students, talk to your physics teachers if you want to understand the ins and outs. So I'm not a physicist. I'm not trying to make any attempt to discuss the meaning of these 4 equations in the context of physics. But I do point out that the first 2 statements, I clear all this kind of stuff, that the first 2 statements are about the divergence and curl of E. So these 2 guys are about the divergence and curl of E, and the second 2 are about the divergence and curl of B, of the magnetic field. So that's sort of the tie-in in what we've been doing. So why do this? So here's this punchline. So our only purpose in mentioning these matters is to try to make it perfectly clear to the student that the mathematics we've been doing in this chapter has profound, important applications in physical science. So the Nobel Prize winning physicist Richard Feynman devoted the first 21 chapters in his lectures to the meaning and implications of Maxwell's equations. So 21 chapters of his talk is on Maxwell's equations. That's a lot. So at one point he memorably remarks, and here's this interesting quote. So from a long view of the history of mankind, seen from, say, 10,000 years from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. The American Civil War will pale into provincial insignificance in comparison with this important scientific event of the same decade. And so what Feynman is saying is that Maxwell's equations are a really big deal. The American Civil War, where fought for the freedom of slaves, ended slavery in America, will seem insignificant. Now, I don't know that that's true, but as Simmons concludes, in making this provocative comment, perhaps Feynman was carried away by his ebullient, like over-the-top enthusiasm, but perhaps not. And so I conclude the material part of this class with this reference to Maxwell's equations, with this quote from Feynman, with this extended quote from Simmons, because I wanted to remind you that what you've been doing isn't just a whole bunch of games on a page. It's just not numbers jumping around a page, but what we've been doing has profound and important applications. It's profound and important applications in physics and in the rest of science, or in other places in science. It's mysterious. It's not clear why this calculus that Newton came up with when he was in quarantine during, the Black Plague or whatever, somehow also connects to electricity and magnetism. Like, that's mysterious. That's crazy. That's why you're reading the article by Wigner. But it's a big deal. I think that human life is important, and so I hesitate to, especially at this time and place, to say that the American Civil War could ever seem insignificant. But I think that the point's important. So that's the end of the material. I think at the very end of my page, I included one more thing. The end. Like we did it. We finished calculus. You got some homework assignments, but you did it. And so I'm excited. I'm proud of you all for making it through. This has been a long quarter, an intense quarter, and you all made it.
What's PTO?
PTL, that's a note for myself. It stands for Praise the Lord. And so, but thank you for that. And so here at the end, as you know, I try to end every day with some sort of a blessing, something to send you off on. Usually they're humorous. Every now and then they're serious. But as we're ending this quarter, I thought I would refer back to a blessing from, oh, yes. Evan's asking about milkshakes like last quarter. I would love to have milkshakes with all of you. I'm just not allowed to see you from closer see you face to face. So might have to meet me after the quarter for a milkshake. I'm sorry about that. Yes, I'm a firm believer in milkshakes. But by way of a closing blessing for this class, I think back to something that was written, like a Jewish blessing that was written about 3,500 years ago. And so this is one that is meaningful to me, and I hope is an encouraging send-off as you go into what's going to follow. So this is reads as follows. So it says, "May the Lord bless you and protect you. May the Lord smile on you and be gracious to you. May the Lord show you his favor and give you his peace." So as you leave this class, may you be blessed, protected, feel the graciousness and the peace and favor that is there for all of you. So thanks, everyone. Feel free to hang around if you want to talk about the world or COVID or otherwise. But it's been a blessing, and I look forward to seeing you all one last time on Monday, Tuesday, Wednesday for final exam presentations. Take care, everyone.